It was in meters?
I converted everything to meters.
So you were like 0.00.
Yeah.
Okay.
Yeah, I was converted to meters. But it was basically the same thing.
Yeah, I like how
Still listening to, what is it called, Invest Talk.
On Spotify.
yeah.
It is very special.
Mr. Legends.
Listen, what is it? Like the history.
Okay, everyone, let's get started for today's lecture. So let me first wrap up. In the previous few episodes, we actually is approaching the end of September. Time goes pretty fast. We're about to wrap up the chapter 6 on the textbook. So if you have not read the textbook, make sure you do. It will be related to the final test. The final chapter test that we're gonna give next Thursday, right? Now, this will be the last one for us to discuss about chain conformation, chain statistics in the polymer physics class. So next, this Thursday, actually, since we're a little bit ahead of schedule, we can have a break. Meantime, I will be traveling this Thursday, so there will be no class this Thursday. Next Tuesday, we will start talking about into the next chapter, which is chain solution, chain dynamics, etc. Okay, so I think I will wrap up the chapter 6 in this class, and we can get a little bit head start for the next chapter. So what we're going to talk about, yeah?
What are we doing with the homework?
So you can still hand in. You can just put it in my rest. Right. I will be gone. So at the end of the day, yes, I will be return on Sunday. So Canada. Yeah.
Where in Canada?
University of Windsor, across river of Pittsburgh. Not Pittsburgh. Detroit. Yeah.
Great place. Windsor is.
Yeah. I will try to be hit there before the winter comes. So, that's as I told my friend. I has to be visiting you at the end of September, before October starts. I'll get back to the topic. So what we're gonna do is wrap up the final few topics about chain statistics, and we will use half of the class to do that. And the second half, we will talk a little bit about solution property. Give a head start for the next chapter. Okay. So in the last lecture, we talked about a random walk professor. After he get drunk, he goes back and forth, and we sort of get some ideas if you walk wrong enough what the probability is, right? So we did some of the math and some of the calculation on the board to understand that. So let me jump to where we left it, where since R stands. So in the last lecture, we talked about someone going +1, +2, going back and forth after a couple random work where he's going to be n, and what's the probability. And I spell out to you the probability is nx will be equal to where he took a positive step, where he took some negative steps, escalation mark divided by positive step multiplied by negative step. So the top line will be total number of steps divided by 2 and plus x and minus x, and we can continue to talk about.
Ending up where he started?
No, that's how many ways you can get to the number x. So this means if you take n steps, okay, what's the possible ways to reach x. So that's what these n and x means. X is a number somewhere between minus n and plus n. And n is the number of steps. So if you take n steps, what's a possible way you can end it up there? And this is done by using this equation. And this function basically tells you this is a total of positive step. And this will be negative steps. Okay? Because if you forgot about where you're going to be, what we only care is where you ended up, right? What we only care is where we're going to end it up at number x after n step. Okay, so x is an arbitrary number, right? X is just a number, so you take it. It does not depend on if you take positive or negative first.
And x is a number of steps in either direction?
No, x is a final direction. X is a number between minus n to positive n. X is where you're going to be ended up. Let's say, let me give you an example. If I want to say n equals to 5, so which means I will take 5 steps, x equals to 3 means what's a possibility if you take 5 steps, you will end up in a position 3. X is a position on the scale, right? X could be anywhere between minus n to positive n. Does this make sense? Okay, so what I'm trying to say is if you want to finish up at number 3, it doesn't matter if you take positive 4 steps then take 1 step back. You will be ended up 3. Or you take, this is scenario 1, right? So scenario 2 would be you can take 3 positive, 1 negative, 2 more positive. It will be ended up the same at number 3. At the final x position equals to 3, right? So wherever this negative step you will take, you can take anywhere in between. You will be ended up at the same, minus 3. Correct? Does this make sense to you? So in other words, this is where it comes down to this equation. This is n bracket nx means how many possible ways you can take n steps and it ended up at number x. So let's try this equation. N 5 step, we're going to finish up at 3, right? So this is you're going to take total of 5 steps, and you're going to end it up number 3 will be equals to, on the top will be 5. That's total number of steps you're going to take. Total of 5 different steps. On the bottom, it will be 5 plus 3 divided by 2, exclamation mark, and multiply by 5 minus 3, 2. So I just applied 5 and 3 into this equation. So n will be equal to 5. This will be 5, x will be 3. This is what you will get. So top is still 5, right? How about this?
4 factorial.
Yeah, 4 factorial. This will be 1 factorial, so it's basically 1, right?
Can't you just cancel it and get 5?
Yeah, exactly. You will be able to get it at 5. So what does this mean? If you want to take 5 steps, you will be ended up at the number 1. There's total 5 different ways, and you can see 5 different ways will be take 4 steps forward, 1 step back, and this negative step can be anywhere, anywhere here. So that's 5. Okay, it's easy to understand if you only write small numbers, 5, 3. What if I say n equals to, I'm going to take 100 steps, what's the possibility? Ended up 20. And you can no longer count like this way, right? This is impossible. You're going to take, let me see. You're going to take, what do you know is you're going to take 60 steps forward, right? Forward, right? And take 40 steps backward. So if you do this combination, you will be ended up at 20, and you take a total number of 100 steps. Makes sense to you both, right? So again, let's try a bit. We probably won't be able to write everything down, but let's at least give it a try. And 120 will be equal to 100 divided by 40 and 60, right? And you know where the 40 and 60 is coming from. This is total number of taking backwards. This is total number of taking forward. That's 100 step total number you will get. All right, I won't go through the math, but you got the idea. It will be a lot of possibility you can take, right? So let's do one more step. We're going to expand to a polymer chain in 3D dimension. We're going to take as many as possible step n, and we can count down to where your n chain will be at. So in this way, what we got is just a number of possible ways to reach there. And what we need to do one more step to get to know where your chain is there or not is called probability. This needs to be divided by total possible ways. And we talked about at the end of the last class, the total possible way for all different configurations is, let me write up here, total possible way of a range of moves is equals to 2 power of n. This is basically each step you can take either forward or backward, so it will be 2. And you take n step, it will be power of n. Now we can do one more step, we can get the possibility. Possibility is basically ability of reach x position after n steps will be equals to, someone help me? This divided by 2 of n, right? So that's exactly correct. So you need to divide this by the equation we had here. There is m plus x half n minus x half. And again, n is total number of steps. X is where you will be end at this position x. So these are the way you need to move positively or positive steps. in this, and this is a negative step. And divide by this total number, you will get the possibility. So let's come back to this, and let's calculate this. So what's the possibility of you take 5 steps and you ended up number 3? Let me write here. Possibility of take 5 steps and end in number position 3. This will be equals to 2 power of 5th divided by what we calculate is this thing will be equals to 5. How about this?
36 or
32. Okay, so 5 divided by 32 is roughly about 15%, right? About 15%. Close to 15 is where. So you got 1/6%, a little bit less than 1/6 percentage. You know, if I'm a random guy, then walk around, then in the end there is possibility. So we can do the same math for arbitrary any steps, and I can understand where I will be ended up in the position X. So this is perfect for 2D, right? This is a perfect, actually 1D. So this is a perfect for 1D, but in this case we only have one scale. You can either go left and right. So the real polymer chain is only a little bit more complicated. Instead of going left and right, now your polymer chain can go 3-dimensional. It can go up and down and left and right. But the conclusion or what the mathematics or physics behind all these are the same. You can calculate what after you're taking n segment of your polymer chain. You fix the origin of the polymer chain. Let's look at here to show you example. If we fix original of the 3D-dimensional chain to be 0 position in the x, y, z, then we can just walk around, say this chain has to be going one direction. After n steps, right? This is a particular configuration, but it will be able to tell you a probability of your chain ended up at a certain distance. Let's call it arbitrary distance of s. You can ask, after you take n segment, will your chain end be probably within this distance? Same question if you look at this equation. We ask if we move n segment, what's the possibility you ended up in x, right? X is somewhere shorter than the total straight chain. So in this case, we can ask if S is less than NL. NL is totally straight chain. That's the longest possible length in a polymer. What would be possibility? What's the probability? Let's go probability. Okay, so this is something we can ask. What the chain gonna be like if it's close to 0 or come back to its original position? What's the possibility compared to walking around the distance? What that will be?
So could we not cube the probability? Could we not take this equation that we solved for and then cube that?
Yeah, we can, and that's the point of this class. We're going to talk about that. Use what we learned from 1-dimensional and apply it to 3-dimensional. Okay, clear? So let's first get the 1-dimensional. We kind of know what it is, right? So it's actually not that easy to solve that pretty lengthy equation. So first, let's get a guess about, in this case, the distribution. So let's say this would be 0, and this would be the n step. So the longest possible way, if you take n steps, what your probability curve will look like this, very much like a Gaussian curve. And I'll write down the equation for you. This is relatively easy to understand. If your chain will have more chance to end where it is starting off than it's going along, one direction continuously. So what does this mean? If you say I'm that drunken professor and I'm walking backward and forward at equal probability, the chances of finding me at the same room next morning will be higher than finding me at my house, which is 20 miles away, right? Because you tend to cancel out each other the more steps you walk. So that's exactly says you'll be likely ended up where you originally coming from, which is 0. So compared to the number 1, you will drop a little bit probability. And when it comes down to n step, you always go in that direction. It's very low. Because it's like playing a gamble game. Well, almost every time you have half of a chance to go forward. If you want to take n step, you ended up n is 2 to the power of n1. So if you take 100 steps, you ended up every step you're going forward is 1 out of multi-million chances. It's almost non-existent. So what about this? I won't bore you with all the equations, but I will write down the probability. And you need to know this probability equation is equal to 2 pi mb squared power of 2/3 So this factor is on exponential, okay? So let me talk to you about physical meanings about this equation. So
Is that in absolute?
No, that's h.
H.
H is what the,
Okay.
or we can call it S. Either way, it's the same. Where the end to end, where the distance from the center. Okay, so let's take a look at this sort of complicated equation, but not so complicated. For a given polymer, we know what is mb squared is. This is roughly the end-to-end distance, right? And this big term in front of exp is a constant. It will not depend on what the h is. H is end-to-end distance. So this is a constant. So we can just write as this symbol to mean it's proportional. Okay? So this first top equation will be proportional to only to exp to minus 2mb squared to 3h. And do you guys understand what the exp minus x is related to? What does this function is in mathematics?
Exponentially increasing.
Yeah, so let's first draw out what it would be y equals to exp minus x. So exp is exponential. So before we take that step, let's have y equals to expx. That would be basically mean y would be exponentially increase. E would be somewhere between 2.6, and it will be just exponential increase, right? So y equals to minus ex, you can write as 1 divided by expx. So this is basically saying you quickly drop to infinitely approach 0, because 1 divided by a large number is very close to 0, right? So this will be the E. So now coming back to this equation, what we will see is if you increase the h, you will have a rapid drop in this probability function. In the chance you find your chain, the highest is where it's closest to where the original spots, right? And there is another interesting fact about this chain. If you consider the average probability of your chain, if you do the integration of the function, so the average of probability finding the chain will be equal to exactly mb squared for this equation. So in a few sentences, what we did here is we understand, let me take this way, that probability of finding end-to-end distance plot as value related to mb, this will be h, or vector, or we can call it S will be probably easier for you guys to understand. That's a vector distance from where the original spots. This would be probability of finding it. And as you would see, this will be, my hand drawing is getting better. So it's, again, it will be Gaussian distribution, similar to that. If you use a computer, you can plot this thing out, and you can exactly see what would be the probability. So how do we use this equation? You can use it in many ways. You can calculate what the probability, for example, find the chain at the original spots, which means this value would be equals to h equals to 0, or where you have original spots, right? So if you put 0 to here, this factor will be 0, and exp 0 will be number 1. So this value will be just 2 pi mb squared 3, the probability of you hitting here. You can also see what's the distance, say, if I want to end up at end-to-end distance h. H will be mb squared. Let's say this spot. What will be the probability here? You can do that, right? So you can just put in mb squared in this equation. H squared is now, h squared will be equals to mb squared. So they will cancel each other. So this value will be 2 pi mb squared. That's the same prefactor. So this term, it does not depend on h. Then multiply by e, power of 2/3. You can use that to know what's the probability of your final chain. And you can go longer than that. as we know, average distance, end-to-end distance is mb squared. You can see what would be your equals to 2 times mb, or 2 times of h squared. There will be another probability, but it will be lower than what you have. So in other words, if you look at a polymer chain you made in polymer solution, now you measure what would be each individual of the chain look like. In the solution, you will have a billion of the chain. If you pull any of the chain out of 1 billion, you have highest of the chance find it to be, one end very close to each other. You have a slightly lower chance to find at end-to-end distance, and even lower chance to find them at twice of what you calculate in average of that. But if you do the math, okay, we won't do it there. But if you do average out all these abelian chain, what you will get is exactly at this point, which is what we discussed. H squared will be average will be equals to mb squared. That's where this importance of these average sign, because you don't care about one individual chain. You care about collectively a time average property of this abelian polymer chain in solution. Okay, so this would cover what we call it probability of finding an ideal chain. And again, I will always want to emphasize the reality is a little bit different. The probability in this case is peaked at 0, while in real chain, you won't be able to find the highest chance where end-to-end distance is touching each other, because your chain will occupy a volume. It will not be able to do that. So your probability will shift a bit to be a value that's slightly higher than what 0 position is in real chain. We won't talk about this in this particular course, but you might want to have this in the mind, that the longer the distance, it's again agrees with what we derived from, ideal chain will drop. Okay. So, in other words, what we learned in the first 5 lectures is very important. The last lecture was just putting a little bit the explanation, cherry on the top of the cake to explain some of the confusion that while we draw something like on the board, do we already know the end-to-end distance? You know only one chain, but you need to really care about average chain, and that's what we talked about. So up to now, we concluded about the first chapter for ideal chain. And we can now take, again, a 5 minutes break. Then we can come back. If you guys have any question, we would like to go through the chapter 6. It would be a good time. Otherwise, I will start to introduce the next lecture. It's about polymer solution property. OK?
Chapter 10, right?
No, 7. Not yet 10 yet. I could teach 6, 7, and there's one more is elasticity.
What's he doing?
Just inside the lab.
Distracting people.
Taking the Buffalo Wild Wings.
Supervisor's the best.
That lunch did not fill me up. My lunch gave me stomachache.
Haven't had lunch? That's a pretty late one.
What?
Haven't had lunch yet?
No, I've had lunch.
Okay.
It wasn't
Just
I was
first
saying
lunch.
it's not filling. Yeah. Second lunch it's coming after this class.
How did you like the new teaching schedule? Like have a longer class and a shorter class?
Not a huge
We used to have teach 3 times a week. Monday, Wednesday, Friday for 50 minutes
That would
each.
be very helpful for especially the mechanics course. So we have it twice a week, sometimes for like an hour.
I would
Right.
prefer 3 days a week because even though we don't
Yeah.
have much to do on Friday, it's like all the days would be shorter throughout the week, so like we kind of space out
Right,
nicely.
right.
It's like, I feel like I haven't seen you in so long.
Yeah, what I feel is, I feel like longer classes also keep the student attention into the same
Yes,
subject
no.
for 90 minutes is challenging.
Because after about 35 minutes, everyone's attention span kind of goes
Right,
downhill.
right, exactly. So good to have the shorter class.
'Cause
My
when
same
it was,
feeling.
50 minutes, we would have. So on Monday, Wednesday, Friday, we would just have. So did they have Tuesday, Thursday classes
Yeah, we still had Tuesday, Thursday classes.
They still have it, but it's just the No, I mean they used to have the other way. Tuesday, Thursday would be the shorter class. Tuesday would be more like lab once a week. You would teach the lecture for the laboratory calculation, then you follow by a lab course. It doesn't need to be repeated 3 times. That type of class will be
So if it
either.
was normal, would we have had all 4 classes Monday, Wednesday, Friday?
No.
No,
We still have
no,
Tuesday, Thursday classes.
yeah.
Okay. Interesting. Oh, 3-day-a-week classes were an hour and 10 minutes, and the 2-day-a-week classes were an hour and 45 minutes.
Mm-hmm.
Was at my school, which is like pretty intense, but
Yeah, yeah. So the graduate class has been, I feel, less intense than undergraduate, especially junior, senior years, kind of to be intensive 2, 3.
Here, I don't think I would like be done for the day until 8 p.m.
Right.
You had to meet for like 1,000 things. Class and lab.
Yeah.
Just don't remember it.
Well, because if you have like if you take a couple science classes, that like adds so much like time to your week. So it's like
Oh.
So 5 science
Mhm.
classes a semester before semester.
Oh.
it's really hard.
Yeah. Okay, let's get a little bit head start for the next chapter. I, use the next 40 minutes. My goal is to give you a general introduction. What is the next big chapter or next the whole October we're gonna discuss about. Oh, by the way, we're 1/3 through the class. Congrats! It's a big step. It's painless, right? For
That was so fast.
it's very easy.
Wow, now
So for the next month, we're gonna be focusing on something totally different with the first chapter. The chapter 1 is sort of you want to study most fundamental basics about polymer physics. All these chains, the model we talk about is sort of like you have a chain sitting in a vacuum, and we usually only study one chain. But in real world, as you see, if you want to use a polymer for any application, a glass, a lid, it's a collective of many polymers. It's not just a one single chain. We need to care about its end-to-end distance, or what will be how rigid the one chain. Of course, that will be matter. Later on, you will see individual do matters, and a collective individual will be influenced by that single, polymer chain. And so for this second part of the class, we're going to talk about is more fundamental on a very unique probability of polymer is compared to other material is they actually can be processed in a unique way, namely by solution process. So in other words, your polymer can be dissolved in a solvent and then later reshaped back into the format or the shape you wish to have. And a lot of other related polymer property will be discussed as well. For example, in many cases, polymer you are not used necessarily in the solid phase. A lot of time you would see or interact with a cup lid for your cup or a plastic in your calculator, etc., or a trash can. But in many cases, some of the unique things you would encounter is, for example, if you're taking medicine, let's use that as an example, you would digest the pill and dissolve your material and start to circulating medicine into your body, right? In that case, the solution property is equally important compared to your single component property. So in this particular lecture, we will dive into the beautiful word about polymer solution. We need to understand a few key phenomena. I will talk about one of the most important theory you would probably study in the polymer physics, polymer solution is called Flory-Huggins Theory. We will understand what is that theory is about. So I'll give you a disclosure about that theory is it talks about the phase behavior of mixing two polymer. Okay? So why we care about that, in many cases you would not just use a single component of polymer in any engineering product. In most of the cases you need to improve the property A while without sacrificing property B, so you want to get the best of both worlds in terms of, for example, impact property together with optical property. Sometimes it's harder to do both, so you would opt out to do blending system, okay? So in this lecture, we will also learn, part of that is how can we understand from polymer physics perspective if the polymer will blend or not blend. It's like mixing oil and water. They would never blend. They will always phase separate out. But if you mix ethanol and water, they tend to be blend very well. Same argument would make sense for the polymer. If you mix polymer A and B, what the phase diagram will look like is what we're going to study. So in a few words, by the end of chapter 2, you will learn if the polymer will mix or not, and if they will likely to phase separate or not phase separate, and what's the reason they would phase separate or not. So the first lecture about chapter 2 will be very broad and kind of introductory, and I want to just to get some college physical chemistry class with you guys. You guys all studied it, right? Thermodynamics, first law, second law. Any one of you can help me maybe refresh myself. I has been out of college for a while. So what is that about? In a few words. Anyone?
Systems deteriorate towards disorder and increase in entropy.
Entropy. That's one of the terms I feel is one of the key for the thermodynamics, right? This is a key term we will talk about constantly in this class is entropy, which is S, the symbol. So entropy is a very vague term, please. And the other related is enthalpy, is another term. You will, yes, we will get into that. Free energy. Those are very So these three terms we will start to interact and talk in more details in this lecture. So let me refresh you guys what is entropy means. State of disorder. I found it's very...
The number of possible states.
I got a good feeling about this second part. Chapter 7 will be easier to teach than vectors, etc. Right? Everyone knows this is proportional to disordered state. So it's a parameter that measures how disordered it is. If the entropy is higher, so S is higher, that means your system is more disordered. Right? So it's just a, tidiness or clumsiness of your polymer structure. So in other words, your system wants to go to more disordered state. So it's like a fundamental polymer, not only polymer problem, it's like a general physics problem. Everything will go into disordered state. My kitchen, my living room with the baby there, if you don't work on it, it tends to go to maximize disorder state, which means your toy will be scattered everywhere in the room, possibly in my office where I'm gonna paperwork scattered around. So you always need to put in work to reduce disorder. That's the first part, is entropy. I think everyone get a clear handle of that. How about enthalpy? Correct. That's related to the heat generation in the system. Can you speak louder a little bit?
Q, which is heat, times C, which is specific heat, equals enthalpy in some cases, or it's...
Right. So enthalpy, you're talking about a case very specialized how much heat is generated inside system. So let me first generally introduce this is about the heat in the system. So this is a parameter that talks about is there any heat change if the system gives out heat or taking heat while it transits from one state to another. Some of the general understanding is you would experience in the chemical reaction, there's some endothermal, right? Some of the reaction, they actually generate heat, like mixing water with concentrated sulfuric acid, which tends to be dangerous, but it gives out a warm final product you would experience. That's a great example that gives out enthalpy. So that's related to the heat, and we will talk a bit more in the following few lectures. How about this?
Likelihood of the process to the likelihood of process to undergo.
Spontaneous.
And then if it's G naught, or delta G naught, it could be whether the whole reaction is reactant favored or product favored.
Okay. I feel I don't need to teach this lecture anymore, right? Fantastic. Way easy. I like it smooth. So this means delta G, which means free energy, is less than 0. That means spontaneous. We want to do a reaction that's just to call it spontaneous process. So it will be generous process. So this will be happening as a breeze. You don't need to work on it. It will happen by itself. Okay. So there's actually several ways you can express this delta G term. Delta G is a free energy, right? So we could, what if we think about an imaginary process? Yeah, that's would be one of the Gibbs equation, where delta G will be related to H and S. Before we go into that, let's think about imaginary curve. This would be G. This will be just the states. And let's define a few different states. What is a stable state? Equilibrium, or quasi-equilibrium, or what is totally out of equilibrium. I didn't hear you, but let's try this. Let's give it a little bit deep. So what this means, if you have put a ball in here, it will be stable, but it's not the most lowest energy for the whole system, right? Where you would see, think about this as a hill or a mountain, where at the high state where you have high energy, we call this type of energy is called metastable. If you pass this state, you can lower the system to even lower state. It will be perfectly happy if this is in here, right? It will be the lowest energy state. Let me give you an example what that would be. Now think about this eraser, and I'm going to put it on my desk or this desk. There's many ways I can lay it, right? And there's different states. What would be the lowest energy state I put it on? Laid flat, right? So this would be lowest energy. It will be resistant to tiny little bit energy perturbation or disturbance. What that means is if I tilt it a little bit, it will come back to its original state. So in other words, so let me expand this a little bit. Draw a little bit symmetric to that, sort of. So if you think about this is where I laid this in flat. So if I give a little bit perturbation either way, it will come down to where the lowest energy state. What would be the metastable state? It's sort of.
What's that plate called? Metastable?
Yeah. Meta is META stable. It's sort of not so stable, but localized stable.
That
And
lowest point is metastable, is that what you said?
no, this is a stable state.
Can you spell it out? The META?
Yeah.
Like
There's many ways people would call it, but you can think about it's not so stable, but it's temporarily stable. Example, it will be laid upwards. It's sort of stable, right? If I don't do anything to it, but if I tilt it a little bit, let me tilt this way so I don't mess up your desk, it will drop down. Compared to if you lay it flat, either way, you won't have any change. So this you can think about if I lay my eraser upwards, if you give it a little bit perturbation, so if you're gonna tilt it slightly, it's gonna fall down to here. So another different state. The way I want to introduce this, because later on in this lecture, we will go through these phases. In real world, while you're mixing the two polymer, you actually can experience this state. Well, this is definitely called unstable state, right? So let's give it another name. Unstable, because you know you're going to spontaneously come down to form a low energy state. So throughout the lecture, we will learn several different states of mixture of materials where mix of two polymers can be in the unstable state, which means once you mix them, for example, you agitating them with a stir bar, for a night, then they will look very much homogeneously. But if you let it sit there without any stirring, it will spontaneously phase separate and form two different polymers. Okay, that would be quantified this. This is a sort of understand if you have two materials, they're gonna mix, and whatever you do to it, heat up a little bit or shake it, still behave as one phase. That is, we call it stable state. And you will learn, interesting enough, there's something happening at metastable state. It do exist for polymer blends where you have a perfectly mixed two-phase, but you change a little bit temperature. Let's say you heat your solution up or cool it down a little bit, it's spontaneous phase separate. And this, you will learn there's many scenarios with some interesting term. We will discuss in more detail. We call it critical temperature, or higher or lower than this temperature, your material will no longer be mixed, and we will talk in more detail. Okay, so this is a good illustration for you guys to see what's the energy state, or if your material is stable or not. Ultimate definition is coming down to here is delta G. Okay, that would be the state. Anyone of you are not so comfortable about the thermodynamics, I really suggest you to take a look about your college PChem textbook, and we can discuss that. So now, I'm going to start to introduce a little bit about what is polymers, if they are mixed or not mixed. So let's study the first part is polymer solution is about mix or not mix. Any one of you watch a very interesting YouTube channel called Blend or Not Blend? It may be not so interesting. There was a crazy guy, he just buy a blender or a fluid blend, then he put all the random things in to see if it's blend. Not exactly the same, but we will see if it's mixed or not mixed. So what we're going to do is we're going to come up with the idea when your material will start to mix. This, again, coming from the last lecture where we learned polymer solution is a little bit tricky to deal with. Polymer is sort of long. There's entropy of the polymer will be harder to calculate, right? Because you have longer chain, and what different state is hard to direct interpret. Enthalpy that I will come down to, and we can talk about that. It depends on interaction of your molecule. So we will take the same approach as we did first. We will start with a simple case. What would be the simple case you think about in this case? Easiest thing to understand the mixture of small molecules, right? Ions would be similarly simple. It's just a one. But since we are talking about polymer, let's don't consider ions can be more complicated. There's charges involved. And we want it as simple as possible. So let's think about a simpler case. Let's consider a scenario as solvent mixture. A and B. Okay, so if you want to know if solvent A and B would mix or not, you can look up the polymer handbook and see they are mixed, but that's not the point for this class. That will defeat the purpose. So we will consider two very generalized cases. Now I'm going to do some tricks. So think about polymer solvent A is each solvent molecule A and B are same size, but this is apparently bigger and not fair to B. So similar in size. And B, we make it a white color. A is black color. Then let's consider the ideal case, if they will mix or not. So you guys did me a great help. If they will mix or not, all we need to care about is delta G. Good job. So delta G will be, let me think, it will be enthalpy minus temperature multiplied by entropy. So you will consider delta H is heat difference in the two, and delta S T is just the temperature.
Delta T? S delta T, not delta ST.
Oh, could be. Yep. So this will be talking about entropy contribution, but interesting enough, entropy will be related to the temperature difference. So in the case of mixture, now we're going to do two parts. This lecture will not be able to cover all of them, but let at least consider one part is enthalpy. So let's consider delta S first. And I will reintroduce you Tom Brady again. But not that Tom Brady, but Tom Brady for polymer physics is Flory-Huggins. He is the most famous MVP in polymer physics. You will learn again and again, okay? So he is in the 1950, and he has many interesting ideas and concepts about polymer solutions. So how can we understand delta S? It's such an abstract term. You mix a solvent A and solvent B. How do you calculate the entropy difference?
The difference between the molecules when they're reacting with themselves versus when they're reacting with each other.
That's more like enthalpy. We will come to that. Interaction between these two different molecules will come down to enthalpy. And I'll introduce another famous player. He's not the sort of a football player, but he's so famous, I'm sure everyone knows about that. There's Einstein equations. Turns out to be related to all the polymer physics. You know, he's lucky enough because he was born after Einstein, so he already has some theory he can work on. So total entropy for a system is directly proportional to how many states it's possible for the system to take. It's a little bit tongue-twisting, but I will let you think about. It's the total possible state your system can adopt. Yeah, exactly. Totally position point. So we will call it, this is Flory invented as a name. He didn't call it a Flory theory. He just called it, very simple to understand, the lattice argument in terms of mixing. A question in the back? Yeah, good. We will get there. Very good call. He already took my job. She already took my job. So entropy will go up. But we will figure out how much it's really go up. Because the conclusion makes sense that you cannot create disorder. If you mix a red color ball with a green color ball, you have two hands, each hand has 10 balls. You mix them, the disorder is increased, right? The degree of disorder is increased because your system is more disordered. You have a mixture of two. The other way you can think about, why we need to recycle garbage is we need to separate them. It takes time and takes someone's effort to separate material A, B, and sort them out. So reverse of sorting or mixing will be always increased entropy. And the goal is for us to figure out why and how big the entropy increase while we mix A and B. Use the rest of 10 minutes or so. I'll introduce the concept for you guys and how we can really use what we learned in early of this class to understand that. How much entropy loss? Or we call it entropy change while we consider when we mixing, let's call it polymer A and B, and we need to specify how much total materials are there. So let's say we total have Na. That's the number of molecular for the first solvent. This is solvent B, okay? So we're going to mix those together. And this is the total number of them. Ma is just how many of them. You know, it could be 10. Let's give us some numbers for you to understand. So in one case, it could be just 100 molecular of solvent A mixed with 100 solvent B, 200 solvent B. Then we can see how much entropy change. You can calculate exactly how much is that. So as we talked about Einstein and Boltzmann, these are two of the very greatest polymer physicists, not polymer, physicists in general. Total is the conclusion for first part. Entropy is equals to K multiplied by L ln this simple omega is related to total, possible states of orient. So we can just say it's total possibility, total number of molecular arrangement. I will explain what does that mean. And K is a constant called Boltzmann Constant. It's a physical constant. You can look it up in any physics book. So K line omega will tell you what the entropy is. So all we need to do now, this is a constant, so it does not depend on what material we mix. And omega is related to how many total states. So all we need to count is how many states of your chain of your solvent will be having before you mix in. So now we consider you have a beaker A, which has 100 or Ma number of molecular A around, right? So this is number. You can think about if you say it's 100, there will be 100 molecular solvent molecular around. Mix with B, which you have Mb solvent B molecular around. Let me write it as solvent A. So you have the mix. Then you will create a bigger box, and the total number will be A plus B. But now you have A and B molecular everywhere in this case, right? So how do we tackle this? Total number of arrangement. It's it? Very carefully. Great, I like that. We needed to be very carefully, but how careful is very carefully? You will see in a moment that we need to figure out how many of possible states. So we need to know number of molecular arrangement possible in A and arrangement in B. We can calculate what is SA and what is SB and SA plus B, right? That will be the final, and your entropy difference will be SAB minus SA minus SB. So that's a final state. That's individually state before you mix them, correct? So now we need to really carefully figure out what these individual states are. Well, it turns out to be not bad. And this carefulness will only be translated to this omega. And I will not be able to finish all of them, but I will inspire you to think about what this is. And Flory basically says, why don't we consider this to be a box? A will be a box made of different grids. How many boxes is here? 1, 2, 3, 4, 5, 6, 36, right? Boxes. And now let's say we have, instead of call it 100, let's call it, we're gonna have 36 molecule of solvent A. Okay. And let's assume solvent A is a white dot. So we can just need to fit in how many different way of arranging these dots here. Then we can tell what the S entropy is, right? So each of them will be in this box theory or lattice theory, different way of filling each molecule will represent different disorder states. Yes, if you totally fill it, but let's assume they are slightly different for each molecule, then they will be different, right? In this case.
So A is not uniform?
No, we will get into A is uniform, but this is indeed just one state. He is exactly correct. So this will be just one configuration. So that value will be 0. Same for B case, right? Because it's the same molecule, whatever you fill it in this box, they will be always take the same state when you fill these dots. Same for B. If you take 36 boxes, they will be the same. But how about A plus B? Now your volume needs to be considered to be bigger. Assuming your each individual solvent A versus solvent B, you're still going to have the same amount of numbers. Now, the total lattice they will occupy will no longer be 36 boxes. It will be 72 boxes, right? And I won't be able to draw every single, let me do that. I think we got some time. 1, 2, 3, 2 more lines. And I'll only draw the first few of them. Okay, now it matters for the S states depend on log in epsilon. We need to consider how many totally different states you can arrange the A and B in that 72 boxes. It's actually not that hard. We already learned in the early of this class. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay. So, what would be this? 72
plus 36 factorial?
Geniuses. It is exactly the reason and the number, let me see, K. Exactly, that would be the entropy state for the second one. I need you to explain why this is happening now.
I don't think think I can. So it's just the total number of possible configurations.
Right.
Divided by how many each of them can like take up.
Interchangeable. Yes, yes, exactly. So 36 is interchangeable for white, black molecular A, so solvent A. This will be solvent molecular B, and this will be another 36. Think about it as a way that, the way you the term they different takes into fill in, doesn't matter if you fill this A or B first. But that's exactly the answer. So if you are a little bit confused with this, I suggest you to start with simple one. Play with 4x4 box. You mix 4 molecular of A versus 4 molecular B to form a 2x4 box and play with it. The argument is the same. If you look at this equation, the total number of possible ways is the same as when we take the random work. It will be total amount of work. You need to take a positive work. This is negative work, right? So in other words, this can be generalized for mixing. N is just a number of molecular A versus M number of molecular B. You can get entropy will be K ln MA plus MB and MA multiplied by MB. And we can explain in more detail in the next lecture.
So we learned this whole walking thing in chapter 6, but we're using it in chapter 7. Does it apply to like other things as well?
I wouldn't call it we learned this thing in just a chain statistic. It's basically just a fundamental statistics because they are dealing with the same problem. How many possible ways you can place, 36 white ball, 36 black ball into 72 boxes, right? So the question we talked early in the class is, if you need to place, 10 positive walk, 20 negative walk into the total of 30 possible walks you need to take, how many number of walk you can take, right? The essence of these two statistics is the same.
Okay.
Does it ring a bell?
Yeah.
Okay, so entropy of mixing into the MA and MB. It will be just an introduction for you guys to think about mixing A and B into the lattice. Well, in the next Tuesday, we will get into more details about how to understand this entropy in terms of before and after mixing and how we can get the delta S. Okay? Cool?
I clapped.
Huh?
I clapped, I don't know why.
Okay, good, good. All right. So
我今天想说的是，让小国道歉，不是直接道歉吧，也得让他们给个说法，事实体现出屈服。那这种外交的强势风格呢，已经不是个案了。我想，随着国内的经济形势越发严峻，显现出的问题增加，这种战狼式的外交逼小国道歉的事件呢，还会增加。因为小国的屈服，它能够满足一部分群众那种大国威严、凛然不可挑战的心理，能满足这个需要。从而它对消费降级啊、什么网络金融暴雷这一类事情呢，就更加可以包容了。看啊，政府在国际上这么保护我们中国游客啊，真给中国人长脸，到处都能感受到祖国的强大。你看中国游客在国外受辱，我国政府虽远必诛，给我们讨回了公道啊。那什么 P2P 暴雷啊，不就损失个几十万人民币吗？所以要看正面，要看正能量啊！你看政府为了维护中国人的尊严，多么尽心尽力啊！ 那点损失相比之下就不足一提了，它就是起这么一个效果。因为现在需要转移注意力的事情太多了。刚刚又有文件说，地方融资平台也允许破产了。那买了城投债的那些非国有机构的投资者就要当心了，在这个地方融资平台的破产清偿过程中，你们肯定得往后排，你们当中至少有部分人会加入到金融难民的行列了。因为国内矛盾越多嘛，那今后这种战狼式的外交吸引注意力的做法可能也会增加吧。那今天这个话题呢就聊到这儿，谢谢大家。最后介绍一下，明天在我会员网站的特别节目专栏播出的节目是明清海禁的原因我们从国际环境的变化来探讨。至于在 YouTube 上面呢，我们就是星期五再见了。大家好，今天是2018年9月17号星期一。今天早上我在准备这集节目的时候，最大的悬念就是大家都眼巴巴地看着川普会不会在今天推出针对中国那2000亿美元的关税大招。在早上6点过的时候，川普还发表了一篇推文，说这个关税是让美国在谈判当中居于强势地位，让几十亿美元和许多工作都回到了美国。同时，这个成本的上升还没有被显著观测到。如果那些国家不愿意和美国进行公平的交易，那就对他们加关税。那这篇推文呢，是川普很快就会推出对中国加关税的一个新的迹象。很多媒体也在预计这个事情在近几天就会发生。那我在准备这集节目的时候呢，还没有消息可能很多朋友看到这集节目的时候，这只靴子已经落地了。但是关税这个话题呢，我们还是等消息落实以后再来聊。今天我们来关注的是范冰冰失联的事儿。范冰冰她在中国可以说是有双重社会角色，第一就是她是演艺圈名人嘛，第二就是她是中国的富豪之一。她去年的收入是3亿元人民币，在影视明星当中是排行第1的。那么对范冰冰的整治呢，也有2重意义。第一，整治她是整治中国文化圈运动的一部分。除了影视行业之外，游戏行业也在整顿吧。另外有一个消息挺有意思，就是一个叫做反骨的乐队因为它这名字里有反字，犯了忌讳，被迫改名叫做正骨。但是我们今天呢，主要还是从范冰冰的第2个角色出发来谈，就是范冰冰作为中国富人圈的拔尖人物，她麻烦上身所反映出的政治和社会意义。其实呢，走出影视圈你也会发现呢，最近掉入麻烦的富豪大有人在。你像王健林的万达公司，还有安邦海航，最近1-2个月，他都有在政府压力之下出售资产的行为。所以你从整个社会层面来看呢，中国的富豪阶层，他和政府的关系正变得越来越紧张。